Hello everybody, Mr. Waz here, and welcome to another episode of WasleyScience. In today's episode, we're going to be talking about the water cycle, the hydrologic cycle. So be ready to talk about condensation, precipitation, transpiration, evaporation, and lots more. So let's get started. Let's start where water originally came from. Now, as we watched from the video earlier this year, we saw that early Earth was a big ball of magma. There was no atmosphere and there was no oxygen. The magma actually did contain water in it, as well as meteorites were pounded into the early Earth carrying water. Water escaped from this magma as it cooled and formed an atmosphere. At the same time, meteorites were continually hitting Earth and carrying water. And these pools of water eventually became the oceans. The atmosphere then cooled the Earth until it could exist on the planet, until water could exist on the planet as a liquid state. And then volcanic activity still introduces a little bits of new water into the atmosphere, as well as some meteorites still carry some new drops of water, but pretty much the water that we have here on this planet has been the same for millions and millions of years. And it's interesting because some people think majority of the water from Earth came from the magma. Other people think a majority of the water came from the meteorites that crashed into Earth. So that's still kind of an argued thing today. Alright, here is the most basic form of our hydrologic, aka water cycle. You can see we have the precipitation. Over here, this is rain coming down, and then infiltration is when the water goes down into the lakes and rivers, streams. We have snowmelt and runoff, plant uptake, transpiration, and then evaporation from the lake, condensation on cloud droplets to form clouds, and then back down again. This is a diagram that you do need to draw. Please pause the video and take time to draw this diagram very well. We have here the same kind of diagram. You don't need to draw this one, but you can see how different diagrams show different things. This one is a little bit more detailed than the last one. And this diagram is even more detailed than the last one. It includes sublimation, it includes fog and dew, and vents and volcanoes, and groundwater storage. You know, the water cycle starts off as a very easy thing from the first diagram you drew, and then you have this diagram, and then you can even get more complicated. I don't expect you to draw this diagram. I don't expect you to know everything on this diagram, but this just shows you that you think the water cycle is a very easy thing, but it really is complicated, and earth scientists and environmentalists and everybody are still trying to figure out how it works to this day. There's still so many unanswered questions. So now what we're going to do is we're going to talk about each stage of the water cycle. And one of the most important ones is actually water storage. Most of the time, water is not even really moving along the water cycle. It's just being stored in the ocean. It's just sitting there chilling, not doing anything, moving around from the currents. The ocean is the main storage of water. It stores 96% of the water on our Earth. So all the lakes, rivers, streams, glaciers, all groundwater, that's 4% of the Earth's water. The sea level goes up when there are less glaciers, and currents move the water around the ocean. Some currents are stronger than others, of course, and then don't forget about the global conveyor belt, which moves the entire ocean's water around. Our next stage of the water cycle is evaporation. 90% of evaporation comes from oceans, lakes, and rivers, but the other 10% comes from plants through a process called evapotranspiration. And evapotranspiration is a process in which plants soak up water through their roots. So they soak up the groundwater through their roots. The water travels up the plant for photosynthesis to occur, and then eventually the water makes its way to the leaves or the branches of this plant or tree or whatever it is, and then the water is released through the leaves of the plant through evapotranspiration. So the water goes from a liquid state inside of the plant and escapes through the plant as a gas. And that's where 10% of water, how 10% of water goes into the atmosphere. Evaporation cools the environment because it's absorbing heat. And the rate of evaporation can change depending on the relative humidity. If relative humidity is at 100%, the air has reached its dew point, and at that point, condensation will occur. So what you can do now is you can watch these two videos on the bottom to kind of get a better understanding of what the dew point is and what humidity is. Now that you've watched those two videos on humidity and dew point, condensation will be a little bit easier to understand. So condensation is when the temperature has cooled to its dew point, the water will begin to condensate, and that means go from a gas stage to a liquid stage. And this is why you would see dew in the morning time as opposed to hotter parts of the day. And as this gas stage, water vapor rises, it will then condensate onto particles of dust that are in the sky, in the atmosphere, and form clouds. So I do have something a little depressing to tell you, that clouds aren't these big fluffy things in the sky that if you got shot through a cannon and then went through a cloud, it would show your outlines of your body or something like that. They're really just giant piles of dust with water droplets on them. That's all they are. And when you're inside of a cloud or whatever, you don't even really notice that you're in a cloud. So yeah, I'm sorry to tell you that. But anyway, the higher the altitude, the lower the air pressure. And pressure is just the amount of molecules in a given volume, which we discussed earlier this year. And what this means is the higher you go up, the less molecule collisions there are, which leads to a lower temperature. And a lower temperature will then lead to water going from a gas stage to a liquid stage. And then, of course, clouds can be moved by the wind in the sky, in the atmosphere. There are many different types of clouds, depending on the altitude that the water droplets and piles of dust are, depending on the amount of evaporation that's going on, and depending on the temperature, the amount of sunlight in the day, and even the amount of wind. Our next part of the water cycle we're going to talk about is precipitation. This is when water becomes released from the clouds in the form of rain, freezing rain, sleet, snow, or even hail. And what happens is at first the cloud droplets will not fall from the sky, but eventually there's so many water condensating on the particles of dust that it becomes too heavy to exist in the atmosphere. And one raindrop is really millions of cloud droplets that have collided and collected together. The amount of precipitation that we have on this earth depends on the geography. And you can see here in the diagram below that the lighter color represents areas that do not really receive a lot of rainfall, which makes sense that the west side of the United States is a lot drier, as well as the top of the continent of Africa. And then you can see there are some areas that are very rainy, like the rainforest in South America, as well as the Indonesia area. A concept that I want to add to our precipitation discussion is called orographic lifting. And what that is when you have a large mountain right by the ocean, and this is caused from two tectonic plates colliding in a subduction zone. You have a large mountain, and then you have a cloud that is trying to get up the mountain. And the cloud can't make it all the way to the mountain, so it has to take some weight off of it. It has to bail, and thus it precipitates on one side of the mountain. And then, so you can see here, you have the rainy side of the mountain, which we call the windward slope. And on the other side of the mountain ends up not really receiving much water. We call that the dry leeward slope. We also call this area a rain shadow. So this area ends up being very dry, and this area ends up being very wet. And one of the perfect examples of this is you have sunny California, and then you have Nevada over here, which is on the other side of the large mountains in the United States there. And it ends up being very dry and desert-like. So you have two totally different climates right next to each other, but depending on what side you are of the mountain, you experience a different amount of rain. Now we're going to talk about runoff, and the first type of runoff we're going to talk about is snowmelt runoff. And you may be thinking, oh, snow, how much does it really do? It actually does a significant amount, because every spring the snow and ice from colder regions will melt, and that will make its way into the groundwater and contribute to the water cycle, and contributes a huge part to the water cycle. Large amounts of water will rush down streams and rivers from the colder areas and replenish the water cycle with fresh water. And you can see here on the diagram that a little bit after January and before July, every single year, there is just this surplus of water that occurs into stream flow. Our other type of runoff is surface runoff, and this is just when water from rain flows into saturated grounds or impervious material, and then it flows downhill. Only about 1/3 of rain over the land event leads to the ocean. The other 2/3 gets evaporated, it gets soaked by plants, or it just gets stored in the groundwater. And you may be wondering what impervious material is. Impervious material means that it's getting stuck on top rather than flowing through. Now we're going to talk about a little bit about groundwater. So when you have precipitation, you have snowmelt runoff, you have surface runoff, you have infiltration occurring at this time, and that's when the ground is soaking up water. And the amount of water it can soak up depends on a couple factors. One factor is porosity, and porosity is the amount of space between the grains of the material. So take a look at the diagrams on the bottom here. You can see on the right we have low porosity, so there's a little amount of space between the grains, and then you have high porosity, which you can see from those circles. There's a lot more water that can flow through the space, and you can see it in here as well. On the left diagram, it shows the pores in which water can flow between the sand grains or dirt grains or whatever it is. The rate at which water moves through the ground is called permeability, and if you have a permeable layer, that means that water can soak through, and if you have an impermeable layer, that means that water is not soaking through that material or that layer inside the ground, and it's just accumulating or collecting on top of it. Water slowly moves underground towards rivers and eventually the ocean. And when I mean slow, I mean really slow. And we call that groundwater, all that water that's below the ground that we can't really see. Let's take a look at a couple diagrams to understand the permeability of groundwater. I can't get you a picture of groundwater because it's inside of the ground. That won't really work. So we have to rely on diagrams for this. On this diagram here, you can see the surface of the earth, and then underground you can see what we call the water table. You'll always see an area called the water table. And what that is the water table does change depending on the amount of rainfall, the amount of precipitation that's going on. If it rains more, the water table will rise, and eventually it could saturate the ground if you have a lot of rain or you have snowmelt runoff. And if it's not raining for a while, the ground table, the water table, I mean, will fall, and it will be harder and harder for water to be pumped out from a well. And you can see here that there's this little drop around the well because the water is being sucked out around the well and at a rate that it's not being replenished. So you can see here that it says days and years, and what that represents is that the water that's around the well directly has only been there for a couple days, but water that's far away has been there for a couple of years. And the longer that water has been in the ground, the more filtrated it has been. And that's good. You want that. You can see here, this is called an unconfined aquifer. So that means it's a area of the water that has not really been isolated for a long time. And then you have this confining bed. This confining bed is what I was talking about before. This is an impermeable layer. So this is a layer in which water doesn't generally go through. Some does though. And if you dig through this confining bed impermeable layer, you will get to another layer of water called a confined aquifer. And the confined aquifer is basically this area underground of isolated water. It's probably very clean and pure. It hasn't been seen for centuries, so it hasn't experienced a lot of pollution most likely. However, it's very deep, and it's also a very important part of the water cycle. It's probably best left alone. We can have another diagram here that sort of shows more components of the water cycle, like evaporation, precipitation, and then you can see that dashed line again. That's the water table. So you can see how the water table runs even with the surface of the lake, which makes a whole lot of sense because this is an area where I'm moving my mouse is an area that is completely saturated with water. We call it the saturated zone, also known as an aquifer. And then below the aquifer, you have usually fractured rock, which is an area that's very difficult for water to go through. Some does go through the fractures and then can make its way to the ocean. This diagram's a little blurry, but you can see again that you have a layer of clay, which would be the impermeable layer, and then on top you have an unconfined aquifer, which would be a permeable layer, and then below you have this confined aquifer, which would be isolated water because the clay, which is the impermeable layer, is separating it. All right, let's talk about the cone of depression. And this isn't the cone that you put on your dog after it's been spayed or neutered or something. This is a situation in which you have pumped so much water from your well that the water around the well hasn't been replenished fast enough, and it makes a cone shape. You can see that cone shape right here. And if you remove too much water and pump too much water out of your well, eventually the cone will drop below your pipe to the well, and you will do what's called running your well dry. This is really bad. It not only damages the pump that you have associated with your well, but you just took all the groundwater. You took it faster than it could be replenished. That's not a good thing. And this happens often in dry climates and in situations when an area has a drought. And you could click on the video over here and it'll talk about groundwater. It's a 5-minute video. It's very interesting. It talks about dry areas of the earth. I highly recommend that you click on this video to get a better understanding of groundwater. The last part of our water cycle is the distribution of water on Earth. And if you look all the way to the left, you can see that 96.5% of our total global water comes from the ocean. And then we have these little slivers here that come from other parts of the Earth, which in 2.5% of it is fresh water. So let's take a look at all of the fresh water on our Earth. That's over here in this second bar. So 68%, around 69% of our fresh water is frozen in glaciers and icebergs, ice caps. And only 30% is actually groundwater. And then 1.3% of fresh water is actually from lakes, rivers, ice and snow, everything that you are familiar with, which just blows my mind that 1.3% of water is from all those huge lakes. That's including the Great Lakes. That's including every lake, every pond, every river, every stream is only 1.3% of all the water in the world. I have 2 videos for you. The first one is on the top left here. It can get you a great review of the water cycle, and what's best about this is it uses the same language that I've been using throughout this video. On the bottom right, we have a video that focuses more on the sustainability of water, and they're both by NBC Learn, and they're really great. You definitely need to watch them. I have 2 more videos for you to enjoy. I have the crash course hydrologic and carbon cycle video. This goes more into depth about the water cycle and even introduces the carbon cycle. So this is a great video to watch because the next unit that we are doing is the carbon cycle. On the bottom here, I have quite a treat for you. I have the entire episode of Bill Nye the Science Guy on the water cycle. Now, I'm not requiring you to watch it. If you need to feel like a kid again and watch it, please feel free. I remember watching this myself when I was like in 5th or 4th grade, but I'm not going to be playing this in my class because I think it's just too basic for us at this point. But hey, if you are really struggling with the water cycle, then let Bill Nye help you out because he's a great guy. Credits for content on this video goes to the USGS on their Water Cycle Summary School. Alright guys, at this point in the video, you should have watched those videos that I recommended to you for review because now you need to fill in the blanks. I gave you this handout. You know it. You have it in front of you. What I'd like you to do is use the notes that you've just collected from this video and see if you can fill in the blanks. Now, if you are completely struggling with this, what you can do is go to my website, go to Unit 5, Water Cycle, and then scroll down to the presentation selection and go to the water cycle and go to the very last slide. It will remove these gray boxes for you, but only use it if you need it. Alright guys, thanks a lot for watching and take care.